Assalamu alaikum everyone. I hope every one of you are safe and home, and we have to start our online classes from today. As you know, we were instructed to take online classes from 29th, and that is today. And I've checked your midterm scripts as well, and I have to say that I expected more from you guys. I thought that each and every one of you would get in the high 20s, have marks in the high 20s, but that was not the case. Most of the scripts that I've checked, they have almost 15 to 20 marks as average. Average marks is 15 to 20, not more than that. One person got 28.5. That's the highest that I've checked. I'll provide you the marks once I've checked all the scripts and documented the marks. I'll provide you your grades. Now, as you can see, I've created a Google Classroom for you guys, and this is the code for the class. If you type Google Classroom and enter this code, you will join the classroom automatically. There is no problem whatsoever. And as you can see, I've already posted some of the documents, some of the materials that you're going to need. Also, there is one assignment that I gave in the last class before everything closed down, before the lockdown. I gave an assignment on chapter 9. The teachers are discussing how to evaluate students amid this crisis, but we're not sure. That's why I'm giving you this assignment. Please do it and scan the problems that you have solved with CAM scanner. I'm repeating again, CAM scanner, and send it to me. You don't have to send it to me. You have to post the document here in the Google Classroom. As for our syllabus, we have already completed chapter 9. There will be a half. Your final exam is 40 marks. I don't know if that's gonna happen or not, but we're gonna plan ahead with that. There will be half question. There will be a half question from chapter 9, and from chapter 10 there will be one full question. From chapter 11 there will be one full question, and as we go on, we'll study some selected topics from chapter 12, chapter 13, and chapter 14. And a quick preview of this chapter, if you would like. Chapter 9 is sinusoids and phasors, and you know most about it, because we didn't cover anything but sinusoids and phasors up to mid. Today we're gonna start chapter 10, and that's sinusoidal steady state analysis. And the contents are nodal analysis, mesh analysis, superposition theorem, source transformation, Thevenin and Norton equivalent. These are called the circuit analysis techniques. These can be used to solve almost every circuit there is. You've been introduced with these techniques before in your electrical circuits 1. Here in AC circuits, the processes are almost same, mostly same, but the difference is the introduction of phasors. As you've gone through phasors already, you know they are complex numbers, and their calculation requires careful handling. The process that you followed in DC circuits will be the same, but there will be introduction of complex numbers, as you know already. After we complete chapter 10, we'll be going through chapter 11. And chapter 11 is called AC power analysis. This is one of the most important chapters. I repeat, one of the most important chapters in your career as an engineer. And the contents are instantaneous and average power, maximum average power transfer, effective and RMS values, apparent power and power factor, complex power, conservation of AC power, power factor correction, and some applications. Chapter 12 deals with three-phase power. I see that you're mailing me for queries and something like that. Someone sent me a mail now. I'll answer them one by one, but I have to record this video and send it to you before the scheduled time. And how this works is, you'll go through the video and take notes. I'll walk through the slides and tell as much as I can through the video, but you'll have to take notes and you'll have to take things seriously in order for this to work. Coming back to the point, chapter 12 deals with three-phase power. You've been introduced with Y delta configurations. Chapter 12 is all about that. There will be balanced Y to delta calculations, balanced del to Y, balanced del to del, balanced Y to Y connections and calculations. Chapter 13 deals with magnetically coupled circuit, and it deals with mutual inductances and power reserved in those coupled circuits, and also transformers, auto transformers are also discussed in chapter 13. In chapter 14, we'll learn about frequency response. As you've seen in the lectures, earlier lectures, the impedance of inductor and capacitor depends on the angular frequency omega, right? As the angular frequency increases or decreases, the impedances of inductance and capacitors changes also. We'll also see resonance if we can cover up to that point. That is, chapter 12, 13 and 14 will cover only the selected topics, because I don't think we'll be able to cover all the topics. At the end of chapter 14, we'll also see filters, active filters, passive filters, high pass filters, low pass filters, and things like that. Now let's start chapter 10. Today will not be a big recording because I don't have a broadband connection, to be entirely honest. I'm doing this with my mobile data. I don't have a broadband connection here in Chittagong. I'm in Chittagong right now. When everything locked down, I came here. Okay. This is chapter 10. The name of this chapter is Sinusoidal Steady State Analysis. What is steady state analysis? That is the first question. Okay. Previously we've dealt with DC circuits. Now we're not talking about that. Now we are dealing with AC circuits, where the circuit is excited by sinusoidal or alternating inputs. There was a question in your midterm exam: define DC and AC circuits. Most of you guys wrote a closed path in which direct current flows, a closed path where alternating current flows. This is not a complete definition. A DC circuit's definition would be circuit excited by, or a circuit which has a source which is constant and time invariant. Time invariant or constant voltage or current source in a circuit is called a DC circuit. And a AC circuit is where the source is alternating or time variant or sinusoidal in motion, or in different terms, a circuit that is excited by a sinusoidal voltage or current source is called an AC circuit. I expected this definition, but most of you wrote that other definition. Okay. The name of this chapter says Sinusoidal Steady State Analysis. Whenever in a circuit we provide a sinusoidal excitation that is alternating voltage or current source, there are two responses. One is natural response. In this natural response is in another term called steady state analysis, and another is forced response or the transient response. Always these two responses whenever a sinusoidal input is given to a circuit. But the transient or the forced response dies out with time, but the steady state or the natural response stays. It does not die out with time. In this chapter we'll be dealing with sinusoidal steady state analysis, and this chapter will be mainly mathematics, nothing more than that. Mainly mathematics, using the circuit techniques to solve circuits. To solve branch currents, solve branch voltages, if you might say, and things like that. Moving on, the contents of this chapter is introduction, nodal analysis, mesh analysis, superposition theorem, source transformation, Thevenin and Norton equivalent circuit, op-amp AC circuits. Applications are capacitance multiplier excuse me, and oscillators. In the fan there is a capacitor. It provides the initial surge of power, you might say that. In fans where capacitor is faulty, you need to give it an initial push. In the application we'll see capacitance multiplier, which is obtained by op-amps, and oscillators are AC. In DC circuit we use battery to provide DC source, but with oscillators we are able to get AC output, alternating or sinusoidal output, which may be used to excite other circuits. And the reference book is Fundamentals of Electric Circuits. This book, Fundamental of Electric Circuits by Alexander and Sadikov. And this chapter number is chapter 10. Okay, introduction. Forced or steady state response of a circuit to sinusoidal inputs can be obtained by using phasors. As you have seen in chapter 9, frequency domain or phasor domain analysis of AC circuits via phasors is much more easier then the analysis of the circuit in time domain. In time domain, you cannot possibly solve for a circuit in time domain. With phasors, it becomes very easy. Ohm's and Kirchhoff's laws are applicable to AC circuits as they were applicable in DC circuits, you know that. And the 6 circuit analysis techniques are noted down, and these 6 techniques can be used to solve almost any circuit. Now, in the inner final term question, there might be question that solve this branch current using nodal analysis, solve this voltage using mesh analysis. You need to solve using that technique, but if you solve using another circuit analysis technique, you will get marks. And steps to analyzing an AC circuit is: first, you have to transform the time domain quantities to frequency domain or phasor domain quantities, each and every element, and then solve the circuit using any of those 6 techniques. And then step number 3 is transform the resulting phasors to time domain. These are the steps. And if a problem is specified in frequency domain, step 1 is not needed. In step 2, analysis is performed in the same manner as DC circuit analysis, except complex numbers are involved. I've told you that earlier. Why isn't the slide changing? Okay, it is changing now. Okay, we need to know some definitions before we move on. Elements in a circuit can be interconnected in many ways, and we need to understand some basic definitions about it. And first comes network. Network is regarded as an interconnection of elements or devices, and networks can vary a lot. A network is basically interconnection of some elements or devices. A circuit is also a network, but circuit is a smaller part of that network. You have to understand that. Circuit is regarded as a network providing one or more closed paths. Then comes branch. A branch represents a single element such as a voltage source or a resistor. It can be any element, inductor, capacitor, voltage source, current source, resistor. Any element is called a branch. Node. A node is a point of connection between two or more branches. Between the point of connection, a point of connection between two elements, basically. A node is indicated by a dot in a circuit. And if a short circuit connects two nodes, the two nodes constitute a single node. And you know what is a loop or a mesh? Any closed path in a circuit is a mesh or a loop. Here you can see the relationship between branches, nodes and loops. This must have been covered in your Circuits 1 course, and you can see the relationship branch equals to loops plus nodes minus 1. Look at this circuit. Here is a voltage source, so this is a branch. Here is a resistor, so this is a branch. Here is a resistor, this is a branch, this is a branch, a current source, this is also a branch. So how many branches do we have? 1, 2, 3, 4 and 5. We have 5 branches. Okay, how many loops are in this circuit? There are 3 loops, 1, 2 and 3. Okay, we have 5 branches, we have 3 loops, and the number of nodes 1, 2. This connects this resistor and this resistor, and these 2 nodes are short circuited with this node. So these 3 nodes are basically a single node, and the ground, and imagine all these are grounded or a single point. This circuit can be represented by the circuit on the right. Okay, we are in slide number 6, guys. Okay, this circuit can be represented by the circuit in the right, and you can see there are 1, 2 and 3 nodes. So 5 branches equals to 3 loops plus 3 nodes minus 1, and 3 plus 3 minus 1 equals to 5. And it's very important to understand what is a branch, what is a node, and what is a loop, because these will be needed in our future steps, future mathematics, as we approach them. Nodal analysis. Basis of nodal analysis is Kirchhoff's current law, KCL, and KCL states that algebraic sum of currents entering or leaving a node is 0. If you consider a current entering positive, you should leaving the node as negative. Sorry guys. We'll see an example of nodal analysis here now. Example 10.1. It says find Ix in the circuit of figure 10.1 using nodal analysis. Okay, we have a circuit here. Ix is there, so we'll have to find out the current in this branch, the branch containing the capacitor. This is the Ix, and our voltage source is 20 cos 40 volt. Resistor is 10 ohm. We have an inductor, another inductor there. Okay, whenever there is a circle, that's an independent source, and wherever there is a rectangle denoting a source, it is a dependent source. Okay, what was our steps? First step is to transform this from time domain to phasor domain quantities. That is step 1, and then step 2 would be solving the circuit for nodal analysis, and step 3 would be transforming the phases back to time domain. Now, it is very important to understand whatever the smaller letter represents and what the capital letter represents. We'll come to that later on. Okay. First, convert all the elements into phasor domains. 20 cos 4t will be 20 angle 0 degree with omega of 4 radians per second. 1 Henry represents j omega L. Omega is 4, L is 1, 4 j ohm impedance. 0.5 Henry also represents j into 4 into 0.5 equals to 2 j ohm impedance. and 0.1 farads 1 by j omega c is minus j 2.5. Now rewrite all those terms in phasor quantities. 10 ohms remains the same, 20 angle 0 degree, or you can write 20 only. The capacitor has minus 2.5 j ohm, inductor 4 j, there is a dependent current source. This would be voltage dependent current source, and this inductor is 2 j ohm. First, okay, let's get back to the original circuit. In nodal analysis, you have to first identify the nodes. Okay, with the voltage source, there is a node connecting 10 ohm and the voltage source, but voltage at that point would be the same as the voltage source, so you don't, and that is not unknown. The unknown part is the node connecting the capacitor, inductor and the resistor, this node, and also this node. This is grounded, so 0 volts. So our unknown voltages are this one and this one, and you should denote that. You should write V1 here or V2 here, or the other way if you want that. So first we mark the voltages that is unknown to us. Okay. Now we apply KCL. First to node 1. Consider this as node 1. Okay. There is a voltage. If that's the voltage source, current will flow from there and alternatingly will come back to this one, but we'll consider only one direction, the original direction. Okay. Current is coming out from this voltage source and going in there. This direction is already given, and we'll be going through this inductor and going through this node, and this direction is already also given, and so the last direction, current direction, will be this way, going to this inductor. And if we apply KCL at node 1, and if you consider this current as I1 and this as I2, it will be I1 equals to Ix plus I2. Okay, I1 will be equals to Ix equals plus I2. What is I1? I1 is a 20 minus V1 is basically the voltage after getting dropped a few voltages here. Okay, so I1 would be 20 minus V1 divided by 10. Here is I1, and Ix would be V1 minus 0 volts divided by the impedance minus 2 j ohm. And I2, this current would be V1 minus V2 divided by J4, V by R. I1 equals to Ix plus I2. Consider this current as I1 and this current as I2. Okay, then simplify it, you will get an equation, and if you apply KCL at node 2, this node, there will be you assigned it as I2, then I2 plus 2Ix, and consider this as I3. I2 plus 2Ix as given here would be equals to I3. Okay, 2Ix plus I2, this would be V1 minus V2 by J4, V1 minus V2 by J4, and this current would be V2 minus 0 divided by 2J, V by R or V by Z in this case. And if you substitute the value of Ix, what is the value of Ix? V1 minus 0 divided by 2.5J. Okay, if you substitute this value and simplify this, you get another equation. Okay. This 10.1.1 and 10.1.2, these two equations can be written in the matrix format like this. You know, matrix multiplications work with row and column, right? Like 1 plus 1.5j into v1 plus 2.5j into v2 will be equal to 20. In the same way, 11 into v1 plus 15 into v2 will be equals to 0. So this is a way to represent these two equations, and we'll be solving using Cramer's rule. I hope you have covered Cramer's rule in your mathematics course. Why isn't this slide changing? Okay. Whenever we have this equation matrix format, we've essentially solved the problem. It's just a matter of finding some values. The main determinant del is equals to this determinant, this determinant, and del 1 is the determinant of v1. You replace this column by the constant values, and then you'll get 20, 0, 2.5j, 50. And for del 2, the determinant of v2, you need to replace this column with the constant values. 20, 0 will replace 2.5j and 15. 20, 0. Now you multiply this minus you multiply this, you'll get this value, and then you multiply this minus 0, 20 into 15, 300. In the same manner, multiply this into this minus 20 into 11. This would be 0, then the remaining term would be minus 220. Okay. Then it's just it's the Cramer's rule. Again, v1 would be del 1 divided by del, the main determinant, and the determinant of del 1 is the determinant of v1. And this way you can find out voltage 1 and voltage 2. Okay, when I solve this problem, the angle of v2 was minus 160 or something. Please check this result. Okay, the current Ix is given by, then what would be the Ix? V1 by 2 minus 2.5j, right? Okay, V1 divided by minus 2.5j. Here is the V1, here is the impedance. You'll get a resulting phasor of Ix. Now the question asked small letter Ix. That means you have to take it back to time domain form. If capital letter Ix was written there, you didn't have to do this conversion. You could write your answer there. But as the question wanted, we need to bring the phasor format to time domain format. 7.59 cos. The original signal was cos in the cosine form. So our Ix will also be in the cosine form. 7.59 cos 40 plus 108.4 degree amps. Now you should try out this practice problem 10.1. Okay, you should do this. This is the same, use the same procedure as this one, as this example, to figure out practice problem 10.1. Okay, now what is a supernode? If if there is a voltage source between two nodes, then those two nodes and any branches between them create a supernode. Okay. In this circuit, you can see there is a voltage source between this node and this node, and all the elements are given in phasor format, so we don't need to do any conversion at first. But there is a voltage source between these two nodes, so these two nodes and into any branch between them would create a supernode like this, and supernode is considered one single node. Okay, if a supernode occurs like this, if a voltage source is between two nodes, there will be supernode, and if there is a supernode, the supernode will act as a single node. Nodes 1 and 2 form a supernode as shown in figure. Applying KCL at the supernode gives, okay, this current is already given as 3 amperes. Okay, as this was the voltage source, current will be coming from here to and going downwards, so this direction is downwards, and the same thing goes for this branch and this branch. And if you apply KCL here, 3 amperes is coming into the supernode, and this current would be V1 divided by minus 3J. This current would be V2 divided by 6J, and also the current in this branch would be V2 divided by 12. If you simplify this, you get this equation. But a voltage source is connected between nodes 1 and 2. So that V1 equals to V2 plus the voltage source. V2 plus the voltage source. Okay. I'm not sure about this equation, but I'll try to come up with an answer in the next video. And if you replace this equation with the previous equation, you'll get the V2 voltage, and that would be 25.78 angle minus 70.48 volts. Now we come to mesh analysis, and basis of mesh analysis is Kirchhoff's voltage law. And Kirchhoff's voltage law states that algebraic sum of voltages around a loop or a mesh is 0. Okay. Excuse me. When you approach a problem with mesh analysis, you should give the proper orientation or the same orientation to all the current, and preferably clockwise direction. Here you can see this mesh. There are 3 meshes in this circuit, 1, 2 and 3, and they've assigned 3 currents there, all in clockwise direction. You should follow this convention, because if you give one current in this direction and another current in the opposite direction, that would not help you. You should try to give all the currents in the same direction, and preferably in clockwise direction. Okay. The question asks us, determine current I0 in the circuit of figure 10.7 using mesh analysis. Okay, mesh analysis করে এই সার্কিটটা সলভ করতে বলছে। Okay. Okay. First, you need to assign currents. mesh currents. These are called mesh currents. And if you look closely, there are many currents, many branch currents. Each and every branch would have a current, right? This 4 ohm resistor would have a branch current. This capacitor would have a branch current. This capacitor would have a current. This inductor would have a current. There is a current source here. This resistance would also have a current. But when you assign mesh currents, the number of branch you don't need to consider the branch currents through all the elements. You just need to consider the three in this case 3 mesh currents. First, assign this current, and this current to your circuit as you need, as required. Okay, this is the circuit. And first, as you've seen, the basis of mesh analysis is Kirchhoff's voltage law. First, we apply KVL to mesh 1. And what would be the what would the equation be? I1 is going through this 8 ohm resistor and going through this 10 j ohm inductor and going through this minus 2 j ohm capacitor. So IV equals to IZ, right? So write the voltages as you go on. 8I1 plus 10JI1 plus minus 2JI1. Okay, this term is found. Now this mesh has 2 other currents flowing through them. This I3 terms goes in this direction, and the I2 terms goes in this direction, and it involves the mesh 1, right? So we need to consider I2 and I3 for that. I3 flows through 10J and it is in the opposite direction of I1. Look closely. I1 goes like this and I3 goes like this. I1 goes from here to here, I3 goes from here to here. So we considered 10JI1 as positive. We consider I3 10JI3 as negative, minus 10JI3. In the same manner, current goes with across this capacitor from I1 goes from here to here, I2 goes from here to here. If you consider this orientation, so the voltage due to I2 would also be minus negative J2 into I2. So this is let's walk through that again. The voltages around the loop, the sum of voltages around the loop would be 0. Okay, I1 into 8, I1 into J10, I1 into minus 2J, but there are 2 more currents. I3 is going in the opposite direction, so minus 10J I3, I2 is also going in the opposite direction than I1, so I2 into minus 2J. So we have got all the voltages in mesh or loop 1. So this is our equation 1. In the same manner, if we apply KVL at mesh 2, this mesh would have 4I2 V equals to IZ, 4I2 plus 20. This voltage is already given, so you don't need to consider anything else, plus 20 angle 90 plus I2 into minus 2J plus I2 into minus 2J, 4 minus 2J I2. This is positive and these are in the opposite direction than I2. So minus I1 into J2 minus I1 into J2, and I2 flows in this direction, whereas I3 flows in this direction. So I3 would also be a negative quantity, I3 into minus J2 and again minus before that. So this is our second equation. For mesh 3, I3 is this current, right? This current. So I3 can be directly written as 5. And substituting IT in these two equations will simplify these equations into two variables, I1 and I2. So you've got two equations again, and using the Kramer's rule, write it like 8 plus J8 into I1 equals plus 2J into I2 equals to J50. Again 2J into I1 plus 4 minus J4 into I2 equals to minus 30J. And then find out the determinant of this and determinant of I1 del 1 or determinant of I2 del 2. They didn't find out del 1. Why is that? Because we have to find out I2, I0, and for that we need to find out I2. We don't need to find out I1 to get I0. So they didn't calculate the determinant for I1. Determinant for I2 would be, this column would be replaced by the constant values. J2 would be replaced by 50J, and 4 minus 4J would be replaced by minus 30J, and then they found out the determinant of I2, also the main determinant. I2 equals to del 2 divided by del, and we found out the current I2. Now I2, we've assigned the I2 as this direction, but I0 is in the opposite direction as I2. So I0 equals to minus I2 and negative of this value. This is the answer, and you should try out practice problem 10.3, and that is similar to this problem. And supermesh occurs if there is a current source between two meshes. Then it would create a supermesh. Okay, example 10.4, it says solve for V0 in the circuit of figure. It is using mesh analysis. Okay, watch here. There is a current source between this mesh and this mesh. So it would create a super mesh right here. You can see it here. It creates a super mesh. Okay. As shown in figure 10.10, meshes 3 and 4 form a super mesh due to the current source between the meshes. For mesh 1, KVL gives Kirchhoff's voltage law gives. Mesh 1 is, they've assigned, first of all, using mesh analysis, assign the currents I1, I2, I3, I4. They've assigned the currents. Okay. For mesh 1, what would the equation be? Minus 10 volt plus 8 into I1 plus minus 2J into I1 minus I3 is in the opposite direction, I3 into 8, I2 is in the opposite direction, I2 into minus I2 into minus 2.5J. We get by simplifying this, we get this equation. And for mesh 2, would get something like I2 into minus 2J, I2 into J5. Sorry. In this mesh, you can clearly see I2 is in the opposite direction of this source, and this source is 3 ampere. So I2 would be negative 3, minus 3. And for the super mesh, what would the KVL be? Consider this loop has I3 and this loop has I4. Okay, then apply the KVL. I3 into 8 ohm plus I3 into minus 4j plus I4 into 6 ohm plus I4 into J5 minus I1 is in the opposite direction as I3, so minus 8 into I1 minus I4 as the opposite direction of I2, so minus I2 into J5 we get another equation. And if you apply KCL here at node A, what do you get? 4 ampere plus I3 equals I4. I3 plus 4 equals I4, right? Now if you substitute these values, this one and this one, in these two equations, 10.4.1, 10.4.3, if you substitute those two equations in, if you substitute the values of I2 and I4 in 10.4.1 and 10.4.3, you'd get these two equations containing two variables. And again, using Cramer's rule, we solve for I1 and I2. This equation can be written in the matrix format in this fashion. Find out the determinants, find out I1, and then our required voltage V0. What would be V0? I1 into minus 2j minus I2 into minus 2j. So minus 2j common nile, I1 minus I2 would be equals to V0. And if you calculate this, you find out the voltage across the capacitor. And the last topic of today's lecture is superposition theorem. And superposition theorem states that in a linear circuit with several sources, the current and voltage for any element in the circuit is the sum of currents and voltage produced by each source acting independently. এটা যেটা বলছে সেটা হচ্ছে যে কোনো ব্রাঞ্চের মধ্য দিয়ে কারেন্ট বা ব্রাঞ্চের অ্যাক্রসে কারেন্ট হবে, যে সোর্সগুলো আছে ইন্ডিপেন্ডেন্ট সোর্স, ওগুলার আলাদা আলাদা কন্ট্রিবিউশনের। যেমন এখানে বলছে যে ইউজ দ্য সুপারপজিশন থিওরেম টু ফাইন্ড I0 ইন দ্য সার্কিট, এই কারেন্টটা বাই করতে বলছে। তাহলে এই কারেন্টটা হবে এই ভোল্টেজ সোর্সের একটা কন্ট্রিবিউশন প্লাস এই কারেন্ট সোর্সের একটা কন্ট্রিবিউশন, নাথিং মোর দ্যান দ্যাট। And you need to consider a convention here, and that is whenever you calculate for one source, you need to neutralize the other source. And how do you neutralize the other source? If you consider for the voltage source, you need to open up any current sources, and if you consider the current source, contribution of current source, you need to short circuit the voltage source. That is a convention. I am repeating that again. Superposition theorem হচ্ছে প্রত্যেকটা ব্রাঞ্চ দিয়ে যে কারেন্ট বা ভোল্টেজটা যায় সেটা হচ্ছে প্রত্যেকটা ইন্ডিপেন্ডেন্ট সোর্সের আলাদা আলাদা কন্ট্রিবিউশনের জন্য। যেমন এই কারেন্ট I0টা would be a contribution from this voltage source and also this current source. And when you consider a voltage source, you need to neutralize the current source by open circuit, and when you consider a current source, you short circuit a voltage source. Okay, this is a problem to example 10.5. Now the solution says let dhorteche I0 equals to I0 prime plus I0 double prime, where I0 prime and I0 double prime are due to the voltage and current sources. I0 is due to the voltage source and I0 prime is due to the current source respectively. To find out I0 prime, consider the circuit in figure this one. If you look at this, they've considered the contribution. They're considering the contribution of this voltage source. So they have opened up the circuit containing the current source. This is a convention. While you consider a voltage source, you need to open up current source, and while you consider a current source, you need to short circuit the voltage source. Okay, so now only this source remains. We are considering the contribution of this source only, and 4 minus 2j would be impedance of this branch, and 8 plus 10j and minus 2j would be in parallel. So find out the equivalent impedance, and then they found out the impedance, and then current I prime would be voltage divided by equivalent impedance. This is the equivalent impedance of this circuit. They found out I0 prime, and this is the contribution. This current is a contribution due to the voltage source. Now we consider the current source. To get I0 double prime, consider the circuit in figure 10.12b, this circuit. Now we are considering for the current source, where we need to short circuit the voltage source. And now current I1, now they've applied mesh analysis here to find out I0 double prime. For mesh 1, I1 into 8 plus I1 into J10 plus I1 into minus 2j, I1 into 8, I1 into J8. Okay, the I3 would be minus I3 into 10j minus I2 into 2j from mesh 1, J8 plus sorry, okay, and they've considered mesh analysis in this mesh. Okay, apply KVL here. V equals to IZ, so I1 into 8 ohm plus I1 into J10 plus I1 into minus 2j. This would become 8j into I1, so 8 plus 8j into I1. I1 and I3 has opposite direction, so minus 10j I3, and I1 and I2 also has the opposite direction, minus I2 into minus 2j. They have written it in they have simplified it here. You would get an equation. For mesh 2, I2 into minus 2j plus I2 into minus 2j plus I2 into 4 would minus I3 into 2j, I3 into minus 2j minus I1 into minus 2j. These are minus into minus 2j, so this is positive, and this is also minus I3 into minus 2j, so this is also positive. So if you got another equation here, and for mesh 3 you see that I3 equals to 5 ampere moving through this branch. I3 is equals to 5 ampere, and if you replace I3 values in these two equations, you get two simple equations with two variables, and if you solve for that, you'd get I2, this current, and I2 is in the opposite direction of I0 double prime. That's why they've done this. Now you've got two currents. This I0 prime is due to the current due to the voltage source, and I0 double prime is the current due to the current source. And if you add them up, you're considering the contribution of two sources, voltage source and current source. And if you add them up, you'd get the current I0, as the superposition theorem states. Okay, this is the end of the lecture for today, and try to solve this by yourself, and you can get in touch with me via email, or also you can also call me if you want. I've given you the number. This is the lecture for today. Try to do this maths. Try to do the maths mentioned in this lecture slides. If you do the maths, you will have a better understanding of this circuit analysis techniques. Thank you very much.